Did the formation of the Moon kick off plate tectonics? Hello everyone, welcome back to Zeey. In this video we try to attempt if the Moon's formation initiate plate tectonics. Subscribe to our channel and follow us. Once referred to by Carl Sagan as the pale blue dot, it was a dust particle suspended in a sunbeam. Earth, it is our native planet. One might be tempted to consider Earth as a constituent of an infinite number of exoplanets, some of which could potentially support life in the Milky Way and the universe as a whole. Indeed, that could very well be the case. Liquid water requires only conditions that are virtually identical everywhere in the universe, and there are two methods to achieve such conditions. Ice can be melted by the internal heat of a star or by radioactive decay. However, it is worth noting that the Earth possesses certain characteristics that at first glance appear improbable to be that prevalent in the universe, despite the vast number of possibilities for their occurrence. These attributes may also determine the habitability of a planet or the extent to which life can progress. The Moon and the circumstances surrounding its existence could conceivably play a significant role in this matter. Moons are not uncommon in the solar system. In fact, the majority of planets have them. However, it is perhaps revealing that terrestrial planets, such as Mercury and Venus, do not typically have moons, and it is believed that Mars' moons are captured asteroids. However, moons are typical in all other aspects. Furthermore, although an exomoon around an exoplanet has not yet been confirmed, there is no reason to doubt that one will eventually be discovered as observation and instrumentation continue to advance. Jupiter is the largest planet in our solar system with nearly 100 moons. Charon, the satellite of even the minuscule Pluto, resembles a double minor planet system more than anything else. However, it is also possible to classify the Earth-Moon system as a double planet. Without a doubt, the Moon is enormous, surpassing Pluto in size and being 27% the size of the Earth. There has been speculation that the Moon's presence may have played a crucial role in the emergence of life on Earth. Although that may prove to be the case in the future, the filter is no longer as effective as it was once considered. The premise underlying this concept was that life first appeared in tidal pools on land. In depressions in the coastal rock, the waves and tides would presumably create placid bodies of water conducive to chemical reactions that are improbable to transpire in the turbulent environment of the open ocean. Although the absence of the Moon would result in weak tides, some activity could still be observed due to the Sun's gravitational effects. In contrast, recent findings in the field of abiogenesis suggest that volcanic hot springs and glaciers were more probable environments for the initiation of life's chemical reactions than tidal pools. However, the function of geothermal vents located at the ocean floor remains uncertain. Both alternatives remain viable alternatives. However, it appears that either could occur without the Moon's existence. However, what might not occur are several additional factors. The Moon controls the Earth, and its formation may indirectly account for the axial inclination of the Earth. This is an area that is rarely discussed, but it almost certainly played a role in the evolution of life on Earth. In fact, the tilt must fall within specific parameters, otherwise it will operate against you. If the Earth were to tilt excessively, seasonal variations would be significantly greater, resulting in an entirely different environment for life and evolution. However, in the absence of sufficient inclination, climate variation is absent, potentially impeding evolution by depriving it of environmental stresses. A world devoid of any inclination could very well be perpetually inhabited by microbes. However, there is also regulation in the Moon's inclination. Without its gravity, the Moon's position would be extremely chaotic and unstable, making it impossible for life to exist. Evidently, we require the Moon. The circumstances surrounding the Moon's formation, on the other hand, do not appear to be typical. It appears to have been caused by a collision, which in fact defined the rate of the Earth's rotation and tipped the planet in the first place. Rapid rotation is crucial for temperature regulation. Had the Earth rotated at a slower rate, temperature fluctuations would have been more pronounced, potentially compromising the viability of photosynthesis. The prevailing hypothesis posits that the material that merged into the Moon was a composite of components originating from a proto-Earth and a Mars-sized object, which were both ejected as a result of the glancing strike characteristic of the collision. Significant remnants of the object, referred to as Theia, appear to have partially survived the impact based on the presence of immense blobs or plumes of material deep within the mantle. However, this has not been conclusively established. Furthermore, isotope ratios extracted from lunar rock samples indicate that the Moon is remarkably similar to the Earth in this regard, particularly with regard to oxygen and tungsten. In fact, these ratios would have been too similar if the two celestial bodies had formed simultaneously, as opposed to one of them being partially composed of the other and a great deal of vaporized material combining as things settled. However, there are also issues with this, more on that in a moment. However, it is safe to say that the colossal collision is the most probable process that led to the formation of the Moon. The alternative hypotheses regarding the Moon's formation pose more significant challenges. An alternative theory posits that the Moon originated from material expelled by centrifugal force from the Earth's crust in its formative years. However, this would necessitate an earthly revolution that was considerably more rapid than what is conceivable. Additionally, although planets are capable of gravitationally capturing moons, to do so at the mass of the Earth would have required a considerably denser and more extensive atmosphere to retard the Moon's motion. Furthermore, in the event that the Moon had originated in close proximity to Earth within the solar nebula, a multitude of geological issues would be readily apparent but remain unseen. The relatively high angular momentum of the Earth and Moon system, which strongly suggests an impact scenario, is arguably the most problematic aspect. Although it may seem implausible, impacts that occur during the formation of star systems are not unheard of. Indeed, this phenomenon appears to have been observed in the galaxy during the 1980s, when an infrared flare emanating from a protoplanetary disk left a nearly one-year-long afterglow in that system. The sole plausible explanation for the explosion was the collision of two massive bodies, albeit possibly not in the same oblique manner as the Earth did. Nonetheless, this contains an intriguing enigma. Consequently, initial computer simulations of the Earth-Theia collision predicted that the Moon would be composed primarily of Theia material and not proto-Earth material. Subsequent models challenge this notion by proposing that a greater proportion of the Moon's composition originates from proto-Earth. However, this approach raises significant concerns due to the notably dissimilar isotopes of zirconium and silicon, which distinguish the planet from the Moon. Unanswered is the query of how exactly this transpired. But another enigma lurks within this as well. As indicated by the presence of seismic zones surrounding active plate tectonic zones, Earth is the only body in the solar system to display this phenomenon. To be fair, the ice shell worlds, especially Europa, do feature terrain that resembles plate tectonics to some degree, but is more characteristic of ice periodically splitting, shattering, and moving. However, with regard to the subduction and movement of enormous crustal geologic formations, the Earth is exceptional. Diverse theories exist as to why this is the case. Terrestrial interior planets, which resemble the Earth more closely than Jupiter or Saturn, provide some insight. Mars is intriguing due to the presence of a stationary uniplate. Without any plate tectonic movement or activity, a weak point in that can generate an enormous volcano that rages for such an extended period of time that it engulfs Olympus Mons, the largest volcano in the solar system by footprint. Mercury initially lost a substantial amount of material, essentially the entire mantle, so the absence of tectonics is not unexpected. However, Venus is an odd one. Although Venus and Earth are nearly identical in terms of dimensions and internal temperatures, plate tectonics does not seem to be present on Venus. Volcanic evidence does exist, although it is not as extensive as that of Mars. On the contrary, the planet appears to undergo periodic deformations and fissures, followed by significant resurfacing episodes. One possibility is that the Earth's oceans are at play here, since the water lubricates the entire process and plate tectonics that would have ordinarily occurred on Mars and Venus would not have occurred in the absence of long-term active oceans. However, another factor might have contributed to the Earth's trajectory: the proto-Earth collision at Theia. Revisiting the purported remnant blobs of Theia that are buried beneath the Earth's surface. These are regions referred to as low shear velocity provinces, and they are anomalously sluggish regions of the Earth's interior where seismic waves travel. An alternative, less remarkable explanation for these regions is that they represent the remnants of Theia, or ancient subducted plates that have sunk considerably into the planet. Those remains might have significantly disrupted the flow of rock within the planet if this is the case. Possibly this would have had profound defining effects on Earth. The potential result of the remnants of Theia sinking beneath the planet was the potential propulsion of enormous columns of hot rock upward, which could have exerted pressure on the Earth's solid crust upon direct contact. A sufficient amount of crustal pressure could initiate the process of plate subduction approximately 200 million years subsequent to the collision that transpired 4.5 billion years ago, during the Earth's nascent stage. Should this be the case, the present plate tectonic processes would be a mere vestige and indication of the collision that led to the formation of the Moon. Additionally, there exist further inquiries. How do the tidal forces of the Moon influence plate tectonics? Although indistinct, force is present. An additional factor is the influence of the Moon on mantle convection. In the absence of this, tectonic processes would remain in a state of constant motion. Additionally, our comprehension of the impact that the Moon's presence has on the Earth's interior remains incomplete, and the Moon's presence may contribute to the strength of the Earth's magnetic field. This has numerous implications, one of which concerns exoplanets. Terrestrial worlds that are approximately the size of Earth and fall within habitable zones may have experienced moons of significant size, suggesting that they endured collisions similar to the one that befell Earth. Then it is possible to hypothesize that plate tectonics is also occurring on those exoplanets, which could influence their habitability, particularly if they exhibit candidate biosignatures. Conversely, if we discover that terrestrial worlds with large moons are uncommon, then the explanation for the vast silence may become apparent. Plate tectonics and a moon are required for the magic to occur. It is believed that plate tectonics is essential for life because they establish a carbon cycle in which atmospheric CO2 emitted during volcanism can be locked up and subducted rather than accumulating excessively in the atmosphere. It was previously believed that this cycle was essential for life on Earth, but more recent research has produced models of exoplanets lacking plate tectonics that can retain liquid water on their surfaces for billions of years, suggesting that life may be possible there. Alright guys, this video ends here. Thanks for watching. Is there anything you like to say? Please tell us in the comments. Subscribe to our channel for more in-depth, recurring examinations of peculiar, intriguing and unknown facets of our incredible universe.